Welcome to The Explainer. We're jumping right into something absolutely mind-bending today, quantum computing. Now, if you've been tracking tech news at all lately, you know there's this massive buzz and, let's be honest, a whole lot of confusion around this stuff. So today, we're going to cut through the noise. We're separating the reality from the hype, figuring out how these wild machines actually tick, and looking at exactly how they're gearing up to completely change the world.
Here's the roadmap for today. We'll start with the quantum computing hype, look at classical versus quantum computing, and then get into the hardware, actually building these machines. After that, we'll hit real-world applications in AI, and finally wrap up with the roadblocks in the future.
All right, Section 1, the quantum computing hype, unlocking unprecedented power. Let's get into it.
So there's a huge reason governments and major tech giants are literally pouring billions of dollars into this. We are standing right on the edge of a fundamental tectonic shift in processing power. I mean, think about this. What if a calculation that would take 10 septillion years on today's absolute best supercomputers could be knocked out in just 5 minutes? Well, in 2024, Google actually unveiled an experimental quantum chip called Willow that did exactly that. And just to put that into perspective, 10 septillion years, that is way, way longer than the age of the known universe. That is the unprecedented power we're dealing with here. And naturally, that kind of unprecedented power translates into some truly staggering financial stakes. Quantum computing is projected to explode into a $1.3 trillion industry by the year 2035. So, yeah, this is definitely not just some quirky science experiment anymore. It's rapidly becoming a foundational pillar of our future global economy. To chase down these massive breakthroughs, the industry is scaling up its workforce at just lightning speed. Just look at the jump from 2023 to 2024. The percentage of quantum firms with more than 100 employees shot up from a mere 9% to 39% in a single year. We are seeing this incredible influx of talent, though, to be fair, they're still racing to close a pretty critical skills gap across the board.
Moving on to Section 2, Classical versus Quantum Computing, the weird science of qubits.
To really grasp why this tech is such a game changer, we have to look at how fundamentally different it is from the phone or laptop you're using to watch this explainer right now. Picture a massive, incredibly complex maze. A classical computer handles this by running down a path, hitting a dead end, backing all the way up, and trying the next one. It's totally sequential. But a quantum computer, it essentially takes a bird's eye view. It can figure out the correct path without having to brute force its way through every single dead end one by one.
The secret sauce here really comes down to the fundamental unit of data. Classical computing relies on bits, which, are strictly either a 0 or a 1. Quantum computing, on the other hand, uses what are called qubits. And qubits tap into the totally bizarre laws of quantum mechanics. They use probability and interference to create these wild, multidimensional computational spaces, collapsing the wrong paths and amplifying the right ones.
So how do they actually pull this off? Well, it starts with something called superposition. If a regular classical bit is a coin just sitting flat on a table, it's definitely heads or it's definitely tails. A qubit in superposition is like a coin spinning in midair. While it's spinning, it exists as a combination of the probabilities of both heads and tails at the exact same time. It's totally counterintuitive, right? But it's only when you stop that spinning coin, when you actually measure the qubit, that it collapses into a definite 0 or 1.
Okay, next up, we have to layer in the concept of entanglement. This happens when qubits become so deeply linked together that the state of one instantly correlates with the state of the other, no matter how far apart they actually are in space. Albert Einstein famously called this phenomenon spooky action at a distance. And in a quantum computer, this spooky action is exactly what allows qubits to scale their processing power exponentially.
And the final piece of this quantum puzzle is interference. Honestly, this is the real engine of quantum computing. Since qubits in superposition act like these continuous waves of probability, engineers can literally design algorithms to make those waves overlap. They're intentionally canceling out the probabilities of the wrong answers, like in our maze analogy, while simultaneously amplifying the probability of the single right answer.
So how does this all come together into an actual computation? Basically, it's a 3-step dance. First, you prepare your qubits, putting them into that spinning state of superposition. Second, you run your quantum circuit. You apply gate operations to entangle those qubits and whip up that interference pattern we just talked about. And finally, step 3, you measure it. That delicate quantum state collapses, and boom, you are left with your highly probable correct answer.
All right, Section 3, Hardware, building quantum machines, superconductors, and deep freezes.
Taking all this mind-bending theory and putting it into the real world requires some truly extreme physics. To keep qubits from losing their incredibly delicate quantum state, they need almost total isolation. We're talking giant chandelier-looking refrigeration units using supercooled superfluids to drop temperatures to a fraction of a degree above absolute zero. That is literally colder than deep space. And at those temperatures, materials become superconducting. That means electrons can move with absolutely zero electrical resistance, allowing engineers to control them using super precise microwave photon pulses.
Now, engineers are actually tackling this using a few different physical approaches. You've got superconducting qubits, like the ones IBM and Google use, which are incredibly fast. Trapped ions, on the other hand, offer much longer stability or coherence times. Photons are basically ideal for secure quantum communication. There are quantum dots, which act as scalable semiconductors, and recently Microsoft made a huge splash announcing a breakthrough in topological qubits. These use a totally new state of matter that could, in theory, make error correction a whole lot easier down the line.
Section 4 now, real-world applications and AI, curing diseases and supercharging machine learning.
So why go through all this trouble? Well, this incredible hardware is being built for a very specific purpose. We aren't going to be using quantum computers to, send emails or watch videos. Our classical computers are already perfectly fine for that. We're going to use them to solve hyper-complex problems, the ones with way too many interacting variables for standard chips. Take pharmaceuticals, for example. Today's best supercomputers simply cannot accurately simulate how complex molecules interact because there are just too many electron combinations. But quantum computers, they can essentially mimic molecular behavior directly. That could rapidly, dramatically accelerate life-saving drug discovery. They're also poised to optimize crazy complex global supply chains, design new chemical processes to break down carbon emissions, and, they have the sheer power to break traditional RSA encryption, which is what secures almost the entire internet today. And that brings us to what might be the ultimate technological team-up, quantum computing and AI. It's an incredible two-way street. Quantum will provide the massive parallel processing power needed to train hyper-advanced neural networks, maybe even pushing us closer to artificial general intelligence. But in return, machine learning is actively being used right now to predict and correct errors in quantum hardware. AI is analyzing noise patterns to keep those delicate qubits stable. They are literally pulling each other into the future.
Bringing us to our final section, Section 5, Roadblocks and the Future. The path to fault tolerance. Look, the hype is absolutely real, but so are the monumental engineering roadblocks standing in our way. Getting to a fully scalable, reliable quantum computer is a massive uphill battle, and the main villain of this story is a little thing called decoherence. Remember how fragile qubits are? Well, just a tiny temperature fluctuation, a stray magnetic field, or even random cosmic radiation can cause a qubit to completely lose its quantum state and collapse. That's decoherence. And when it happens, your calculation is completely ruined. So figuring out how to isolate these systems and developing robust error correction to fight decoherence, that is far and away the single biggest hurdle the entire industry is trying to jump right now. Which begs the big question, when are we actually going to get there? When industry leaders were asked when we'll see a fully fault-tolerant quantum computer, meaning a machine that's large enough and stable enough to run complex algorithms without errors, 72% predicted it'll arrive by 2035. The other 28% think we're waiting until 2040 or even later. So make no mistake, we are definitely playing the long game here. But seriously, look at the timeline and how far we've already come. The famous physicist Richard Feynman first proposed the whole concept of quantum simulation back in 1982. Then in 1994, Peter Shor developed the mathematical algorithm that proved a quantum computer could actually break standard internet encryption. Fast forward to 2023, and IBM successfully demonstrated quantum utility, basically proving these machines can reliably solve certain problems beyond the reach of classical simulation. Now, IBM is fiercely charging toward 200 logical qubits by 2029, setting the stage for that highly anticipated 2035 era of full fault tolerance. I want to leave you with this final thought today. We know that mathematical algorithm from 1994, Shor's algorithm, is just sitting there, waiting for hardware powerful enough to actually run it. When that day finally arrives, the cryptographic foundations of our global financial systems, our private communications, and even national security will be completely upended. This technology is advancing faster than ever, and the quantum revolution isn't just a possibility anymore, it is practically a certainty. The only question left is, will we be ready?